for the recording. So welcome to the Canadian Meteorological and Oceanographic Society's lecture series for Manitoba. So this talk is going to be presented by Jay Anderson, and you see the topic there being the weather travel advice for solar eclipses. So without further ado, I'll hand it over to Jay.
Thanks, Pat, and welcome to all of you whenever you're viewing this. Join us this afternoon or at your leisure. And for a number of years, 40 plus, I've been making up climatological studies about places to go to watch a solar eclipse. And it seems like kind of a niche thing to be doing, but in fact, there are tens to hundreds of millions of dollars put into a travel to solar eclipses, particularly in more recent years after the 2017 eclipse over the United States that brought in something around the order of 100 million people to watch it. Now, the problem you have with solar eclipses is multifold, and I'll go into some of that. Talk about where I get the information that I need and what we do with it. In addition to providing climatological advice, I also travel to the eclipses and provide meteorological advice on site. Let me just get rid of this fella here. Now, the first eclipse that I did was one that went top of me in Winnipeg in 1979. So in 1978, I prepared a little document about what the cloud cover typically was like across the southern prairies, because that was where the thing passed and went over top of Winnipeg. Climate information mostly relied on surface observation at the time. Since that time, there's been an enormous explosion in climate information. There's been a huge change in the way information is shared. And personally, there's been a huge advance in computer software that allows me to make up maps of weather parameters and of the track of the eclipse. And then since that time, I go beyond working with weather, and now I actually help manage some of the eclipse tours that go on. So what I want to do is a brief background, talk about what somebody traveling to an event, which is weather sensitive, time sensitive, and location sensitive. I'll talk about the differences in data collection and display, take a look at what we're doing now and why we want to have the sort of high resolution information that we are in search of. When you think about a solar eclipse, by far and away, the most important thing is whether or not the skies are going to be clear. You're going to see an event. The one that I'm going to see next month lasts for 1 minute and 15 seconds. That's reasonably short for an eclipse, but I've been to eclipses in the past that lasted for only 15 seconds. At the same time, the longest eclipse I've been to was just short of 7 minutes. So in either extreme, you're very, very limited and very demanding on your meteorological conditions. So we want those clear skies. We want temperatures that aren't too extreme, and that means too cold or too hot. We have a couple of challenges coming up, and we've had some in the past. I'll talk about those in a bit. We want good visibility. The last eclipse I was at, the sun was about 2 solar diameters above the horizon. We needed a clear view right down to the horizon. And this is especially challenging because clouds always appear much more thick, much thicker, much more opaque as you get down toward the horizon. So you're essentially, for something that's within about 10 degrees of the horizon, you want an almost clear sky. Precipitation beforehand, we don't want that because it upsets the setup of telescopes and things like that. Got a cat here. And winds are a bit of a problem because if they're too strong, they make telescopes vibrate and picture taking gets to be difficult. If I'm an eclipse tour operator working on a tour to go to an eclipse, then the first thing I look at is the long range climatology. Where are my chances best for getting the conditions I want, in particular, where they're most likely to have sunny skies? How hard is it to reach the site? We've had sites that were on beaches in Madagascar that could only be reached at low tide. We've had sites in remote parts of Uganda that where there was little or no accommodation that we didn't bring with us. We've had special camps set up and so on and so forth. At just about any kind of challenge you can imagine for traveling at an eclipse is present when you get into some of the more obscure locations. Once we get close to the eclipse, we have to provide short-term forecasts. And typically that would mean satellite images if you're really short-term, or modeling if you're sort of within a week or so of the event, in order to do things like make arrangements for buses for quick movement or change the location of a ship. We also have to make sure we have a view of the sun, and at least one occasion I know of some group that positioned themselves in such a location that the sun disappeared behind a distant mountain just as the eclipse was beginning. And on top of all of the meteorological challenges, you also have those of normal travel with a large group. The group sizes that I normally work with range from about 15 up to 300 in size. Here's one of our challenges. This was a year ago, December, eclipse just barely above the horizon. You can see here on the right-hand side, the path of the ship I was on and how we had to do an abrupt turnaround just before this picture was taken in order to keep that horizon clear. It was a bit of a challenge and a last minute thing, but in the end, we did manage to see the eclipse. This was in the Southern Ocean, sailing toward the Falkland Islands. Some eclipses are easy. This was in Svalbard, which is in Spitsbergen Islands, about halfway between Norway and the North Pole. We're almost 80 degrees north here. Spitsbergen Island or Svalbard is kind of a challenge because when the wind direction's off the water, the temperature can be -2, -3, and if it comes out of the north, it can be -20. In this particular eclipse, the cloud was not a challenge on the left here, but temperatures fell from -16 to -22 during the eclipse, and there were quite a large number of people who had computers to control their cameras. The computers worked just fine, but what didn't work was the screens. They get too cold and they just go blank, and so nobody knew where the mouse was and was able to control the equipment. In the one on the right-hand side, that was an eclipse in Madagascar, in Uganda. That was an extremely short eclipse, so we had to make a little bit of a last minute 2-kilometer jog to make sure that the sun was in that opening in the clouds that you see there. And it would have been visible if it had been in those cirrus clouds up above the sun. But even so, we like to get as good a set of conditions as we can when we're taking clients to this event. In the early days, most of the information that they got came from surface stations. And this particular plot from the 1980s shows an eclipse. And I believe it was an annular eclipse, meaning that the sun didn't completely get covered by the moon, but left a ring around it. But you can see what I've plotted here is the frequency of cloud cover. This is actually comes from an aviation data set that broke the surface observations up into 1/3, 2/3, and overcast, sort of a scattered, broken overcast collection. And so I plotted the frequency of the clear to scattered cloud here. Mexicans have a very good surface network that allows me to put together a chart like this. But even so, it's still rather broad, and it doesn't really show you much in the way of the influence of the Sierra Madre Mountains. Let me just get up a laser pointer here. The Sierra Madres come down along the whole coast here, and there should be pretty good evidence of lee-side clearing, which is sort of vague in this area. Although certainly there are areas in here, Torreon, which have pretty high frequency of scattered cloud. And in fact, I'll be going right in here next year to see an eclipse. Everything was drawn by hand at that time, so I had drafting tables and pens and everything else. And they were published at first by the US Naval Observatory in their eclipse circulars. And later on somewhat better background, they were published by NASA under a sort of project basis. When you get into places with a little less surface information, in this case, you've probably got 8 or 10 stations that report. You get a pretty crude idea of the resolution. So in this case, you could tell somebody, well, if you want to have a good view of this eclipse, just go to the east. But of course, that's toward the end of the eclipse track, which you see right in here. So you'd be essentially watching the eclipse at the sunset horizon. In those days, North America had pretty good cloud observations and sunshine observations, but those were taken down in the US in the 1990s and almost gone in Canada now. But the rest of the world does tend to have, wherever they collect them, at least some pretty good sunshine observations. So you can actually put distinct numbers on the probability of seeing the eclipse. Here's a map from more recent times now, and in this case, the information on cloud cover is taken from satellites. With the demise of cloud cover reports across the United States, their auto stations don't record any cloud beyond 20,000 feet. So essentially the entire cirrus cloud cover is ignored. So they're not reliable anymore for determining whether skies are scattered, broken, overcast, or whatever. And in fact, that data set is so bad that airports within sight of each other, one of them can report an 80% probability of clear skies in 1 month, whereas the other one would report 39, and so they're totally unreliable. The satellites themselves have problems, but they're relatively consistent regionally, so the biases that they have are manageable. And I tend to treat a chart like this as a chart of relative cloudiness rather than absolute cloudiness, so that we can see in this particular eclipse track, which is coming up later this year, that moving into Nevada will get you a higher percentage probability of cloud based on past climate. It's not really probability, but we'll treat it as such. Whereas if you're getting up into the Oregon, Washington area, you're into about twice as much crowd. And that makes sense. We've got the 2 mountain chains in here that wring a lot of the moisture out of the cloud. Not much evidence of the valley in through here. You get a look at the terrain in that area that got the Cascades and the Coast Range with the valley up the middle. In summer months, this valley is very prominent in the cloud cover statistics with a lot of clearing from the downslope off the Coast Range. But that previous map is for October, and by then the big weather systems are starting to come in across the north. And so the influence of the mountains disappears. Because terrain's so important, I always make up topographic maps to show the eclipse track, because a lot of the discussion that goes with the presentation, which is on my website, a lot of the discussion references terrain. And so resolution is important to see some of the terrain effects. Cloud cover is the element that I spend most of my time on, and in the sort of global data sets that are available, there are probably, if you went looking really, really deeply, probably 10 of them that you could find, but a lot of them are sort of project based, meaning they would only last 4 or 5 years. So what I look for is long-term cloudiness data sets that cover a minimum of 20 years. And that's now easy to do, but back in the 1990s, the best you could do was about a dozen or 15 years. The very first climate data set I used was cloud cover, was a Russian one, which a team in Russia day by day looked at global satellite pictures from polar orbiting satellites and extracted by hand the cloud cover estimate in 5 degree by 5 degree squares around the globe. And now you can see on this chart, the CM-SAF data set is at 1/4 degree resolution. There are two others. Hers is a 1 degree resolution. Down the bottom, the NASA Earth observations are available in a multitude of resolutions up to 1/10 of a degree. That makes a very large data set that becomes a bit challenging when you collect 20 years of data at 0.1 degree intervals covering the globe. You're looking at Excel spreadsheets with 120 million pieces of data that you have to process. And Excel is capable of doing it, but you don't mess with it while it's doing it. The standard is the ISCCP, which is used in climate modeling for the most part, and it's traditionally been around 2.5 degrees, but relatively recently they've switched over to 1 degree resolution. There's a lot of geostationary satellite data in that one, which is pretty limited for my purposes, although I've used it in the past. At present, I like the CM-SAF one at the top because it's a European data set. It's got EUMETSAT support. It doesn't disappear when a university project is ended, such as the HERS data set. And I believe that it gives a little better representation of the actual cloud cover. The NEO at the bottom from Mach-1 Terra satellites is a little bit too cloudy for my liking in high cloud areas. It has no problem showing average cloud amounts of 98% in some locations, which is unrealistic. The advantage of Terra and Aqua satellites is that you have 2 passes, at 10:30 and at 1:30, and you can do sort of morning charts or afternoon charts. Some of the others, Patmos X, which is ongoing, but they've quit providing monthly climatologies, and it's just a major project, PhD level stuff to extract daily observations from individual satellites. There's a private group who have a university group called Earth Environment, and they have a 1 kilometer resolution data set, which I've attempted to use several times. It's huge files for it. And GeoTIFF is a geographic TIFF file, meaning it's a TIFF file with latitude and longitude information embedded. Unfortunately, no program I found is able to open that GeoTIFF file, including my global GIS, Global Information System software. I use polar satellites because geostationary satellites don't reach high latitudes very well. Here's a typical cloud chart produced from the HERS system, which is one of my favorites from about 10 years back before they ended the program. And it certainly gives you some pretty good global impression of what the cloud cover is like. It's a little bit coarse, but it's not particularly visible in this kind of a display. When you zoom in on it a little more, you start to see a little more contouring, although I can smooth that out readily enough in the software. And certainly this provides us with a much better basis for planning than the original hand-drawn charts. We get into small areas in Hawaii in 1991, there's a distinct climatology in Hawaii on the sort of upwind and downwind sides. It doesn't show particularly well in this coarse data set, but it does show up on my 0.1 and the 0.25 latitude resolution charts. You can see some signs of the downwind effects, the clearer cloud in here. So the wake effect around the island and what 14 to 15,000 foot mountaintop in there. But typically this side should show a much lower cloud cover average than on this other side. Here's a high resolution data set. This is from the CM-SAF people. And you can see here the beautiful resolution of the water courses in South America with the higher resolution. And of course, this time of year, which is October, this eclipse, the one that's coming up, is crossing over a land that's very much affected by convective cloudiness at this time of year. And so the river courses, of course, suppress the convective cloudiness. So with a high resolution data set, I'm able to pull that out. As you can see, there's a rather prominent dry season in a part of Brazil, but this eclipse ends a short distance offshore. So a bit of a challenge. Whether anybody would want to go and position themselves on a river course in the hopes of getting what amounts to about a 10 or 15% lower cloud cover, difficult to say. But somebody in Colombia would certainly head into the mountain valleys between the chains of the Andes mountains here in order to have a better chance at clear skies, and quite a bit better. You know, there's about 30% less cloud cover in that valley than there is on the windward side of the mountains. One of the things that we also get locally from high resolution charts is local variations. And you see that with the eclipse coming up next year, the south shore of Lake Erie, because of the suppression of convective cloudiness, actually gives you about a 10 to 12% advantage in cloud cover. So somebody in Ohio who wanted to make plans to go see the eclipse would be better off deciding to go up to Cleveland. In contrast, if you're planning on watching it in, say, Niagara Falls or just off the edge of the map here, you might find your chances are better. But of course, if you've got mobility, you'll be changing your location with as the time goes on, as you get closer to the eclipse. One thing that came out of the studies over the Gulf of St. Lawrence was the fact that Tignish in Prince Edward Island is more favorable than anywhere else in the Maritimes because of the influence of water as well. And I suspect that the town of Tignish will be chock-a-block full of eclipse chasers when this comes by about this time next year. Maps are one thing. I use graphs too. So this is a map of the cloudiness from the satellite along the eclipse track. In this case, it shows the whole of the eclipse track. So we will be letting people pick out their own location. There's quite a difference in cloudiness in some areas between the north side and the south side of the eclipse track. So this one is along the center line, and you can pick up that information in the map, and I give quite a discussion of it on my website. Speak to me. Oh my. There we go. One of the questions that comes up is what happens with El Nino and La Nina, and this is actually cloud chart differences from neutral conditions, or rather average conditions, and El Nino. So you can see the increase in cloudiness along the red band here, and during El Nino, some effects in here. For the most part, not much change in cloud cover. They're all relatively close to the zero mark, just small increases, but definitely dry areas. And you can sort of back this up a little bit by going into the NCEP NCAR reanalysis and looking at the precipitation fields, and you find a very good match between high cloud and high precip and low cloud and low precip that matches up quite nicely. Also shows you that most of the rest of the world doesn't have much of an influence on precipitation and cloud cover in El Nino conditions. Kind of an illuminating set of charts to be able to compare cloud cover with precipitation data. I also get questions about aerosols because in some places, particularly places downwind of the Sahara or downwind of the Arabian Peninsula, sandstorms and other visibility restrictions become important. And tropical storms are important. In a month from now, I'm going to be sailing in this area to watch this eclipse. Now, this is a 100-year listing of tropical cyclones, but nevertheless, it tells me that the ship I'll be on will have to be looking out for large weather systems and cyclones that might be affecting the area at the time. Unhappily, if it does turn out, but normally that's a very sunny area on the globe. And April storms are actually quite rare, less than about one every year and a half, 2 years. I use surface data as well. I've talked about this already. We have certainly got some weather information. Mexicans have good sunshine observations, and so do the Australians. And in fact, the Kerguelen Islands, run by France, but they're not very common. Whereas in Spain, for an eclipse coming up in 2027, they have a lot of sunshine observations in Spain. We're able to put those together. And when we get into eclipse time, or when people want to look at typical conditions, I usually send them over to a NASA site, Earth observation, something or other. And you can look at day-by-day satellite pictures over the last 20 years to see the kind of situations you might encounter. So they're all on my website at eclipseophile.com. Anybody can look at them. And I don't get too many hits on that site until we get close to an eclipse. And then I get 250,000 a day for about 3 days. So it's kind of a place to peruse. Everything I do is open to the public, even though I work with eclipse companies, and one in particular, all this information is distributed globally. So we got 2 eclipses, one October 14, one April 8 next year. October 14, you'll have to go down to Four Corners area of the States to see it easily. And April 8 next year, well, I'll be in Mexico for it, but you could keep an eye on the weather and go and pick your spot anywhere, Toronto, Montreal, Niagara Falls, and San Antonio, Texas, wherever you like. So thank you very much. And well, keep an eye out for the eclipse. And there we have it. You can find an email address at the start of this to contact me if you like.
All right. Thanks, Jay. See, Amir's not there. Anyways, thanks again. It was a terrific presentation. And I guess I'm the one that will be asking any questions here. So I jotted down a couple. I think the first question probably people are wondering is how much time do you have to spend plowing through all that information, say for your upcoming workshop, your upcoming solar eclipse this year? So how much time do you spend on preparing for that?
Oh, per eclipse, a few hundred hours. And got it down pretty straightforward. I've spent a lot of time in the past collecting data sets, so now they're pretty much on my own system. They have to be updated year by year, but yeah, 100 to 200 hours per eclipse now.
Yeah, and that's kind of interesting. 200 hours for something that could be, as you say, 15 seconds to just a few minutes. So I admire your effort and your interest in your eclipse chasing.
It's a high tension atmosphere when you're sitting on a cruise boat with 180 people, all who paid $25,000 to get there and are expecting me to lead them into clear skies, which I've been lucky a few times and unlucky a couple of times.
Yeah. And I know, for those that don't know, you're also a storm chaser. And I guess in many ways it's the same kind of results. I mean, a lot of driving, and who knows, it could all be a
Yeah.
failure at the end of the day.
The day before an eclipse is very similar to storm chasing, except that your mobility is somewhat limited. And typically, I'm not only looking after the site where I am, if I'm at the eclipse, I'm sometimes do it remotely from home for a group that might be anywhere else in the world. But I may be looking at my own site and one or two others for other people that have asked for advice. So this means that wherever I am, I need a good internet connection. In ships, I get it, but sitting in a field in Madagascar, it's just not going to happen. So I don't even have information for myself.
And then just one last question. Your work is, it's a very rare type of work. And I'm sure there aren't too many people that are doing what you're doing for solar eclipses. Is there much, say, competition, if that would be the best word, for others who are trying to do what you're doing?
None that I've found. There are meteorologists occasionally that go on trips, and there are people who know where the models are and try to second guess what I'm looking at. It's the same problem you have in the weather office. You can have 8 models to look at. Which one do you believe? So I like to stick with one. But in fact, we're beginning to look at getting somebody to replace me. I've had people ask me if I know meteorologists, and I've fixed people up to go on eclipse trips to do what I do. But as far as a climatology background, nobody's doing that. No need to. I give it away.
All right, then. It's like our time's running out. So thanks, Jay, for a very, very interesting talk. And for people who want to know, this will be posted on our CMOS YouTube channel. So again, thanks for your presentation there, Jay.
Thanks, Pat. We'll see you again.
You bet.